Alright, let's continue General Chemistry Part 26. Now we stopped in the middle of introducing the second example of precipitation reaction, right? We picked up two soluble compounds, calcium sulfate and ammonium phosphate. Alright, and then from the table, because look at this table again. There's a couple of things I want to mention again. Most of those are the anions, right? And most of them are polyatomic anions, and they do not separate in the aqueous solution. They stuck together, go through the entire reaction, but they will combine with different partners to cations, and then form a compound, either soluble or insoluble. The group A all soluble, except there's a few exceptions. And the group B, they form those anions, they form insoluble compounds, except those are the exceptions. Most of them are 1A and 2A alkali or alkaline earth metals, right? But few of them are not completely as exception because they consider slightly soluble, which means very, very small amount, 10 to minus 10, 10 to minus 9, very small amount of the salt dissolving to the aqueous solution. Solvent was based on water, right? And then dissociate. But soon this little amount dissociate, entire solution become saturated with that, cation and anion, and then that little, right, is already too much to be considered as a saturated. No more compound, ionic compound, can further dissociate into cation anion pair. So that is low concentration, 10 to minus 9, 10 to minus 10, right, mole per mole, and then that is the considered as slightly soluble, but sometimes interchangeable with insoluble. Okay, I want to have to mention that. Now these two, I picked up sulfate and then the phosphate. With the ammonium, everything ammonia will be soluble, so that definitely is. Calcium, well, kind of, but with the sulfate, in this case, these three belong to the same family, alkaline earth metal, but not calcium, right? Calcium is not the exception. So this is going to be belong to the sulfate as soluble, right? It's very clear. And now, if these two soluble compounds combine with each other, dissolve in the water and then dissociate, and then what happens is they go through a double displacement reaction. Now we review that basically, and then we are able to, using this table, the knowledge, right? And they call it solubility rules of ionic compound in aqueous solution. I skipped the rules down there, but normally people call it solubility rules, right? The rules. But here we find out we are able to predict the products. Now in the test, upcoming final, we're going to include in this, right? About entire reaction will be the majority part of the final. I would say, because this virus crisis, we try to not go too much about comprehensive exam problems, but majority, the weight will be on the reaction part. So these two we are able to predict because the calcium combined with a phosphate, calcium, right? Phosphate are insoluble. Exception is ammonium and the 1A alkali metal, not 2A alkaline earth, right? So that is feeble difference right here. We picked up. It's very kind of critical because you want to have to use this example to understand how to apply these solubility rules, right? So here, this is insoluble. And this would be forever soluble because why? The ammonium is forever soluble. There's no exception always soluble, right? With anything else to form an ionic compound. So that's clear. So I said the first step is predict the products. We're going to do that in test. And then second is going to be writing a chemical reaction. Now something left off, and because the space, and this should be not a complete reaction equation. Because why? I just forgot to put what? No, it's not forgot, because the space, right? Should be what? AQ, right? AQ for this second product. That is soluble. So if the soluble must be AQ, right? So let's put it a little better, righty. Let me see. How about that? Okay. All right. Now, after we done that, now we did what? We did simply exchange partner. So the calcium goes to what? Calcium from sulfate go to phosphate, and ammonia from its partner phosphate go to sulfate, right? Then we form one compound that's considered insoluble, which is what? The phosphate, the calcium phosphate. But when we did this, what is the chemical formula? Now, this is given, right? What about these? How can we figure out the subscript for each partners, right? The calcium. Now we go by what? Oxidation states. Now you know why it's so important. We've been targeting the concept and practicing how to apply the concept you learned about oxidation state. Now we come to the application now, right? So calcium oxidation state +2. All right. Phosphate is what? The oxygen. Each one is -2, 4 of them, -8 total. But it appears to be outside is -3 anion. So the phosphorus must be what? +5, right? +5. So now if this whole thing in the parentheses we call phosphate is 3 minus anion, and then this is 2 plus cation if lose electron, right? That gain electron. Then 2 and 3 doesn't match 1 to 1. Only you have to go by what is called LCM, least common multiple. What is least common multiple? For the absolute value for 2 and the -3 and plus the 2 minus is 6, right? So 6. So if you use a 6, if you want to get 6 positive and 6 negative, will be neutralized. So 6 positive, God have what? Have 3 of those. That's where 3 come from. 6 by +2. Divide by +2 give you 3, and the -6 divided by -2 give you 2. -6 divided by -3 give you 2. So that's how the 3 and 2 come along. So that's the formula. We correctly nailed it, right? Nailed it. The same thing here. Ammonium 1 plus, sulfate 2 minus. You gotta have 2. That's a little easier, right? So that's how the chemical formula for these two products will be correctly written, right? Now after you did that, then we do what? We do balance equation. Why do we need balance equation? Well, because we have to follow what? We have to obey in nature. We have to obey. The nature obeys, right? We have to obey the nature. And nature obeys what? Obeys the law of conservation of what? Mass. So here, the mass on the left-hand side as reactants has to be balanced to the mass on the right-hand side of the equation as products. Is that clear? So now we have all these chemical formula correctly, but then we have to balance for the coefficients. What a coefficient for the chemical reaction is balanced with the coefficient in front of each reactant and product, right? That is the, what? Basically it's an integer number, right? That is what we call mole ratio. Now the mole ratio, we talked about this so many times now. Finally, it comes. Right, it comes. What's that for? Is for us to find a quantitative analysis based on what? We talk about matter, the chemistry. What chemistry is matter and its change. All right, on the basis of what? Proportionality at atomic level. Check my notes. I say it very clearly. So the mole ratio tells us the proportionality between what? Between the reactants. Based on the number of moles or based on the number of atoms or the different elements, which is with my moles. And even you have a coefficient in front, they just triple and double that, right? It's the number of atoms inside at atomic level. Did I see that? Did I see that? Yes. I'll say that, right? So now we balance it. So while we balance it, while we are doing the balancing, we try to do what? Go my tips. I'll give you tips, right? There's 12 different points, different issues about balancing equation quickly. But I said, if you look the equation, or look the chemical reaction, if the chemical reaction involves metals, balance the metal first. Why? Because metal always cations. Losing electron become positively charged cations, right? And they normally obey the general oxidation states belong to their own family vertically in the periodic table, right? There's not too many, no, we're not talking about transition, right? We talk about major A group, right? They all very, very strictly follow the family 1A, 2A for their oxidation state. So we balance metal has a reason, right? Now if we don't have a metal, then we go by hydrogen. Now in this case, the hydrogen is only coming from what? From ammonium inside this polyatomic anionic cluster. So we do not really need to look into it. We look at the whole thing as one unit of a polyatomic anion, right? And then we balance what? We balance nonmetals. And in my tips, I said leave the what? Leave a monoelemental, right? Dial or triatomic, right? Molecules alone, because they don't have but one element involved, right? Their coefficient change will not destroy the previous balanced coefficients involve another element, because they don't have another element. They're just a monoelemental, right? One element. And then finally we what? We leave what is the last one we balance. The last one we balance is oxygen. Now here I come to another point we mentioned so many times. Why oxygen now? Because we said over and over again, oxygen is the element appear to be very unique in its compounds, its oxidation state. 99.9% of the case with its compound, oxide or oxyl acid, whatever involve oxygen, appear to be 2- as its oxidation state, or -2 as oxidation state, or 2- as charge if you consider as an anion. So that is the reason, because it's barely changed its oxidation state or the charge. We are certain this element, oxygen, is not going to change when we repeat and double check the coefficient during the balancing process. So we leave that damn thing alone at the last. Now here we go. So it does have element as metal element. So calcium is a metal. We balance calcium, right? How many? This on the left hand side is 1, on the right hand side is product 3. So you have to triple this. That's why I put 3 down there, very small 3. It may not showing very clear because the lights, and this is nighttime, almost like 10 o'clock in the afternoon. This is lights and all these halogen lights, and then it may have a reflection on this kind of board. But I'm telling you, this is 3 down there. So 3, calcium balance. Now we go by what? We go by ammonium. The cation again. Cation is a +1 charge. You got 3 on this side because of the phosphate, and the other side we got what? 2. Now if it's 2 and the 3, they do not match 1-to-1 ratio, right? So you go again LCM. What is LCM again? Least common multiple. Now it is not LCD. Try to make sure you understand. That's the difference. LCD stands for least common denominator. Here is not the denominator. We try to find the least, the smallest integer number as common multiple. What is the common multiple between 3 and 2? Right, the 2 right here. 6, right? So if you use a 6, here the 6 divided by 3 equals 2. So you have to put 2 in front. That's the coefficient. And then 6 divided by 2 is 3, so you put 3 in front. So that's where 3 come from, 2 come from. That 3 also doesn't change because this compound, calcium sulfate, does not involve ammonium, right? We don't talk about ammonia now. Now after you fixed the coefficient for these 2, at this moment, we may have to double check, right? According to my tips, right? We may have to double check, quadruple, triple, if I find out, but it may not need it. So we just temporarily, the ratio, mole ratio between the products calcium sulfate and ammonium phosphate is 3:2 ratio. 3:2 ratio right here. For the products, it's 1:3 ratio because the 1 is here. We do not normally use the 1 and put in 1 in front. So that's 1:3 ratio. So temporarily is 2:3 as reactants, and their ratio to the products is 1:3. So 3:2 to 1:3. That's the mole ratio for the entire reaction equation. Is that balanced? Are those coefficients as mole ratio finalized? Let's double check. Then we find out. If we double check, they are because everything fits. So this is mole ratio, right? After government mole ratio, now this reaction, if we talk about the concept of precipitation reaction, that's it. We're done. Even beyond, right? We're done, right? If you don't involve the mole ratio, if you can write an equation we call predicted products, if you see that kind of problem, that's the end of that problem. But we continue because why? We're going to prepare you for the last section of this whole ordeal called the reaction balancing equations and the stoichiometry. The stoichiometry stands for the quantitative analysis for chemical reactions. That is going to be involving what? The coefficients of balanced chemical reaction, because the coefficients for balance from the balanced chemical reaction equation representing the mole ratio between the reactants and products, and then if we apply the gram formula into each of these substances, we are able to figure out how many grams of this and reactants, how many grams of that will definitely produce how many grams of this and that based on their moles. Now that's what we get in there. But here we don't get in there until next part. We are going to get into another part is gonna be also kind of important. We call writing ionic chemical reaction equations. All right. So after we find the mole ratio, we stop here temporarily. Then we get into what? Writing. Writing complete ionic equations. Writing complete ionic equation, right? And that's just the beginning, and then we have 2 more steps afterwards. And then, so what is ionic equation? Ionic means what? You got to involve something can be soluble in the entire process, and then probably will stay soluble as cation and anion pairs, right? In the reaction beaker, we call it, right? And that is particularly important because in this reaction we just mentioned, we discussed, there is one insoluble compound, but the 2 products, one is not insoluble, it is soluble because of aqueous solution status as physical state, right? So, and also begin with both the reactants as aqueous, so it definitely shows us something we call ionic pairs appear to be in the reaction beaker from the beginning to the end, right? But which one will stay to the end, which one not, become part of the insoluble solid, which is clustered into an insoluble solid, precipitate down to the beaker, the bottom beaker. That is considered as out of the solution, out of what? Out of the reaction solution, right? As the products, the real products, we are able to filtrate it, the solvent and the salt in there, and then we can get that solid, and then that in our hand, that's a real product. So that is chemical reaction. It is not just a dissociation process. Did we talk about this, right? They consider as chemical change. So here is writing. So what do we use? We use the solubility rules. If they are aqueous, means they are soluble, right? So those 2 and plus the final, they are soluble, aqueous. So they are able to dissociate, not only dissolve, dissociate into cation and anion pairs. Exactly, I'll slow down because our I watch my own video. Sometimes I talking too fast, and then my voice bounces into the shining, very smooth whiteboard, and bounce back into the small mic in the camera. It blurred into, all right, something you cannot recognize. That is bad. So I'll try to slow down. So now, if we see them aqueous, if they are ionic compound, the aqueous means the cation and the anion inside the ionic compound formula will be 100% completely dissociating to cation and anion pair, right? So now here, calcium, what? Calcium sulfate. So the calcium is going to be a cation, 2 plus, no, not plus 2, 2 plus. This time we're talking about charge, right? Charge, 2 plus. Now let me just remind you. Calcium belongs to 2A, alkali metal, alkaline earth metal, right? Alkaline earth metal, and it has +2 oxidation state throughout its family members. So, but when you talk about oxidation state in the compound, we say +2. But when it become an ionic part of become a cation of the ionic compound, and then dissolve in the aqueous solution, and then dissociate into cation and anion pair, its cationic status will be no longer +2, but 2 plus. All right, let's make sure. And it's aqueous, right? That's the first one split from this. We split from here, right? Then this one split out of the sulfate, and the sulfate become anion by myself. So sulfate become aqueous, and it's 2 minus. Now, this is not completed yet, because why? We don't forget the coefficient. This means one molecule, one formula for iron compound. This means 3. Either this means 1 mole, right? 1 mole of Avogadro constant number of calcium cation and sulfate anion, right? But we are not talking about only 1. We talk about 3 moles, right? Mole ratio. So you have to work. Since out of 3, so you all have to put 3 in front. 3 and 3. Now let me make sure this 3 is a little clear from the first one. All right. Now that's just 1. The second one we have to do the same thing. 2 is infant, right? Coefficient, right here, 2. So you're gonna add, because they both into the same solution, same solvent, become solution, part of solution. They are dissociate both at the same time. They're wandering around and then become what? Mixed, right? So you have 2 what? But 2, that's ammonium. Ammonia in the formula, in this ionic compound formula, already have 3. But when dissociate, all 3 will be separated individually, become 3. But not only 3, because you have 2 in front. So you have to what? You have to double it. You have to double the 3 into 6. Are you with me? So you're going to be 6 ammonium. Now it's 1 plus charged cation. Now the phosphate. The phosphate is 3 minus anion. We already mentioned that the minus 2 to minus 8 is 5 plus 5. Why is plus 5? What is family? Belong to which group? Right, 5A, right? 5A, right? And then what? And the nitrogen, correct? So check it out, periodic table. You bring your periodic table, right? Periodic table, right, for elements. Let me slow down a little bit. So then you have what? You have how many? 2 of them, right? 2. So 2 phosphate, right? And also aqueous. Now here is 3 minus. Now that is entirely considered the cations and anions dissociated 100% from the ionic reactants. Reactant to it. So this is going to be move on as a reaction. So we put arrow right here. Now since we're out of space, we move here, we put another arrow here. In other words, it will continue from here, then turn around and continue to the products. Do you get it? All right. So it's here, all right. Now, what is this? This is a solid or now it's insoluble. It's a solid, right? It's insoluble. So if it's insoluble means it does not dissociate. Even we say it could be very slightly dissociated, 10 to minus 10, I don't know exactly the value for solubility, right? It's going to be 10 to minus 12. Very, very tiny. We consider this almost insoluble, right? According to solubility rules, it's insoluble. We consider this not even, in this particular case, we just consider it insoluble, completely solid with non-dissociation. So we're going to be having, 3, right? And PO4, right? And 2. Now the solid. Precipitate down. Now for the last one, this one, it is aqueous, so it will dissociate 100%. So you have what? You have ammonium. Again, there's 3 coefficients. Here's 2. But here's 3 because why is sulfate only involved 2? But total still have to be 6 because through the balance equation, you know the number of ammonium anion has to be balanced on both sides. 6 has to be 6, so gotta be 6. There's something wrong here. Here also. He's talking too much and then. This is 4. No, it is. Gosh, it is NH4. Something. And there's aqueous. And you have a sulfate. How many? 3 sulfate. Now we'll charge 2 minus. Alright, now it seemed to me everything's taken care of, right? And when I'm talking, I just realized I put maybe the reverse here, but I think the first time was correct, and the second time it was wrong, but reverse. So here is a 3 calcium here, right? 3 sulfate, 3 sulfur right there, and 6 ammonium, right? And 2 phosphate, 2 phosphate. Where are 2 phosphate? 2 phosphate right there, right? 2 phosphate right there. So we are consider this whole thing was completely balanced. Nothing changed, but just split into split those ionic compound into cation and anion pairs. But now we already talked about it last time. There's something different from the left to the right. Physical state, including the formula of chemical formula. But something exactly identical we call spectator. If spectator is not a spectator or not considered as the participants of the reaction, we are able to, they are equal on both sides, identical on both sides, we are able to take them out as cancellation. So what is a spectator? Gotta be ions, right? So